Good morning and welcome back to Dr. Logic Awkwardly Does Logic. Take 3 of this particular video because there's a limit to how many awkward mistakes you can make in a proof before you decide, actually, I should probably start over. So I'm going to give you a proof, and hopefully it's going to be better than the proofs that I gave in the versions of this video you are not getting. So we are now in a position to do basic theorems in our modal logic K. This is the one that has the rules uniform substitution, modus ponens, and necessitation, and has as axioms all of the tautologies of propositional logic and the K axiom, which I will write down so that we have it ready for our reference. The K axiom is the one that says if it's necessary that P implies Q, then it's necessary P implies necessary Q. So it's a distribution principle of necessity over implication. Now, what I'm going to prove to you today is that necessity also distributes over conjunction. And in fact, you can go the other way around. If you've got 2 necessary formulas, then their conjunction is going to be necessary. In this video, I'm only going to do the first one, because I did that one well the first time around, and I will save the second video for the second theorem. What I'm going to do is go through the proof of the starred formula in excruciating detail. I'm going to follow every single step to make it clear exactly how it works to take propositional tautologies, apply substitution, introduce modal operators, and so on. We'll do this for a couple of proofs. There will eventually come a point where having all of these steps spelled out explicitly actually makes the proofs harder to follow. And then I will talk to you about conventions that we will have for kind of hiding some of the steps, or maybe doing a couple of steps at the same time. For instance, one of these will be, instead of writing down an axiom and then a substitution instance, we'll just write down the substitution instance. But we'll get to those conventions later. Let's look at an actual proof. All of our proofs are going to have to start off by citing one of our axioms, either K, which doesn't look like it's going to help us very much at this point because it doesn't involve any conjunctions, or a propositional tautology. I'm going to start with a propositional tautology, the very simple one that if you have P and Q, then you also have P. The rule of necessitation allows me to stick a box on the front of it. So, oops, I need one more parenthesis. There we go. And now there isn't much more that I can do because I can't do modus ponens. It isn't clear what kind of substitution instances I could use. So now I am going to go ahead and write down my K axiom so that I have it for reference if ever I want. So this is K. Now, what you can see is that we have a conditional with an antecedent that is necessitated. We have a formula with a necessity as its main operator. If I can construct a substitution instance of K, then I would be able to do modus ponens on that along with line 2. So what we will do, I'll write out the substitution instance first and then write out the formula. Everywhere that I have P, I'm going to replace it with P and Q. And everywhere that I have Q, I'm going to replace it with P. So this gets us, if it's necessary that P and Q implies P, then necessary P and Q implies necessary P. So now what we have here is the antecedent just is the formula on line 2. So modus ponens allows us to detach this so that we've got necessary P and Q implies necessary P. Modus ponens lines 2 and 4. And this is great because this looks a lot like our target formula. We've got the antecedent that we need, and we've got, oops, that should have another box there. We've got half of the consequent. And in fact, we can run this same sort of reasoning to get the other half of our consequent. So here I'm going to start from the tautology that if you have P and Q, then you also have Q. Stick a box on the front of it through necessitation. So this becomes necessary. Now, I don't have to write the K axiom down again because I already have it. I can go straight to a substitution instance of it. again, I'm going to put P and Q in every place that I have P, but this time I'm just going to leave Q alone. I don't have to do any substitution there. So again, this gives me that if it is necessary that P and Q implies Q, then necessary P and Q implies necessary Q. 7 is the antecedent of 8, so modus ponens allows us to get that necessary P and necessary P and Q gets us necessary Q. So modus ponens 7 and 8. Now, all we need to do is stitch together lines 5 and 9 in order to get our conjunctive consequent. And we can do this just through propositional reasoning. So we'll need to have a couple of propositional axioms and some substitution instances, and then a couple of applications of modus ponens. So the tautology that I want is the one that says, well, if P implies Q, then if P implies R, it follows that P implies both Q and R. So that is a propositional tautology. Let's see if I can get the substitution instance in without screwing up my formatting. So I'm going to do substitution on line 10. What I'm going to do is I'm going to put in necessary P and Q every place that I have P, necessary P every place that I have Q, and necessary Q every place that I have R. So this gets us if necessary P and Q implies necessary P, then if necessary P and Q implies necessary Q, then can I fit it all? Necessary P and Q implies, not quite, necessary P and necessary Q. And one more parenthesis so that everything matches. Now, what we have is a couple of embedded conditionals, but if you look at line 11, the antecedent here just is the formula on line 5. So modus ponens allows us to detach that so that we have if necessary P and Q implies necessary Q, then necessary P and Q implies necessary P and necessary Q. And that has matched parentheses. So this is modus ponens lines 5 and 11. This is also a conditional, and what we have for the antecedent is what we have at line 9. So modus ponens again allows us to get necessary P and Q implies necessary P and necessary Q. Modus ponens 9 and 12. And that is the formula we wanted to prove. So I'm going to stop while I'm ahead, and we will do the converse of this theorem in another video. Until then, take care. See you in a bit. Cheers.